Hello class, this is a re-upload of the video of an introduction to linear programming and finding an optimal solution. I already recorded this video once, but apparently the audio did not work, so I'm very frustrated about that. But I will re-record it because this is very important. It will set up each of the next few videos. And in this video, my goal is to go over the basic terms and describe what is a linear programming problem, what are the constraint equations, the feasible points, and so on, so that it hopefully will make sense as to all of the steps and the procedures that we're doing in the as we move on to some more generic examples. But essentially, what we're going to be looking at here is a situation where our profit function is going to be based on multiple different components. Like, say, for example, my business sells skateboards and surfboards, each of which has a different amount of profitability. And I wanted to know, well, how many surfboards and skateboards should I sell to maximize profit? Um, that would be an example of what we would call the objective function or the profit function, and where we'd often want to say try to maximize that. In these problems, are often our goal is to figure out what's the best answer, whether that be maximizing of profit or minimizing of cost. But additionally, we're going to impose some constraints on these problems, because in the real world, there's often constraints which prevent us from doing something. Like, for example, my profit function might be dependent on two different variables, but sometimes there are rules, like you might not be able to produce a certain amount of skateboards or whatever. So basically what I want to do is I want to walk through the example that's in the textbook and try to talk about why the equations make sense and just kind of give you some of my feedback about it, because there's a lot of terms and things, and I wanted to sort of just cut to the chase and give you a nice solid example. I really do like the example in the book a lot. I just wanted to discuss it in the form of a video. So let's go ahead and look at this problem. It starts on page 299. We consider the following problem. A company produces two types of can openers, manual and electric. Each requires in its manufacture the use of three machines A, B, and C. The table below gives us the time that each can opener needs to spend in each machine in order to produce it. So what it's saying is that to produce a manual can opener, it requires 2 hours on machine A, 1 hour on machine B, and 1 hour on machine C. To produce an electric can opener, it requires 1 hour on machine A, 2 hours on machine B, and 1 hour on machine C. Additionally, each can opener, the profit of producing each manual can opener will be $4 per can opener, whereas the profit for producing an electric can opener is $6 per unit. And so there's a lot of information in that, but in these problems there's always going to be a constraint which would be represented in the form of an inequality, which is why everything from 7.1 is important. And we're going to be often graphing the regions of an inequality in order to try to visualize what we often refer to as the feasible region. But the constraint in this problem, what it says is that the number of hours per month on each of these machines is restricted to, well, machine A we're only allowed to use for 180 hours per month, machine B we're only able to use for 160 hours per month, and machine C we're only allowed to use for 100 hours per month. So basically, we are sending our can openers through these machines. If we could use them as much as we want, it would be a lot easier. But what it's saying is, like, we have a specific amount of time that we're allowed to use them. And we want to know, well, how many can openers of each type should I produce? And in what way could we maximize the profit? Since the profit is dependent on the number of can openers. But as you can see, there's a lot of facets to this problem. And what we want to do is try to build up a system of inequalities and equations to try to figure this problem out. But the constraints in this problem are a set of inequalities which represent sort of the things that we're not allowed to do. So it says to start by letting x and y denote the number of can openers. So that's what we're trying to figure out. How many manual can openers do we want? How many electric can openers do we want? So that's always step one, is to let our variables stand for what it is we're trying to figure out. So we'll let that be x. We'll let the number of electric be y. Obviously, they have to be greater than or equal to 0 because you can't produce a negative amount of can openers. And we restrict them to the integers because they have to be whole numbers, not like fractions or decimals. Um, Additionally, if we're thinking about each of the constraints based on the time we're allowed to use those machines, um, to produce the manual can openers, each manual can opener takes 2 hours to produce, and each electric can opener only takes 1 hour to produce. So if I add that up, what that would give me is the total amount of time that I'm spending producing my can openers through machine A. And we know that the total amount of time must be less than or equal to 180. That was one of the constraints. So what this inequality is representing is, well, this is the total amount of time I'm going to spend on my can openers in machine A, and that total has to be less than 180. And the other the other inequalities represent the constraints for machine B and machine C. Because for machine B, it took 1 hour to produce a manual, but 2 hours to produce an electric can opener. And this would give us the total amount of time for producing all of our can openers. And for machine C, each one only took 1 hour. So if we add up the total number of can openers, that has to be less than 100 because that's the number of hours we have total for machine C. So basically we have a bunch of inequalities, and if we graph all of these together on the same window, that will give us what we refer to as our our feasible region. So basically the next page, page 300 of the textbook, we have each of those inequalities graphed. So we can see x plus 2y must be less than 160 below, x plus y must be less than 100 below here, 2x plus y must be less than 1a. But notice that each, the feasible region is here in white, and it's below each one of the lines because in each case we weren't allowed to exceed that many minutes. And this is kind of like my boundary for minutes for total x and y in each of the different parameters. Additionally, x had to be greater than 0 and y had to be greater than 0. So altogether, we get this sort of geometric object, this polygon, which represents the feasible region. And all that means is any of the points in this region, so say for example 40, 40, any of these points would work. So if I was to produce, and remember what x means is the manual can openers and y means the electric can openers. So if I were to produce 40 of each, that would be a viable situation because I wouldn't take too much time on any of the machines more than I'm allotted. But if I were to pick points outside of the feasible region, that would violate certain of the constraints. So it's kind of like it gives me a shaded region which makes sure that I'm fitting all of the mandatory restrictions that I have. And this is an example of how we use a system of inequalities and what they're useful for in a business context. Now, the last component to this problem is something which I've been ignoring, but has to do with the actual profit. And back on the previous page, what it said is that we're going to get $4 for each in profit for each manual can opener and $6 for each electric can opener. So we could also write a profit function, which is also referred to as the objective function in these problems. But basically, what our goal is to maximize this equation. And collecting all the information we know, notice this is not an inequality though. I have a function of x and y which I don't know the answer to, and I have a bunch of constraints. The goal is to figure out imposing all these restrictions, what value of p is the greatest. And the question is, how do we go about doing that? So from here, the next idea is what we call an isoprofit line. It's basically we could take this line, basically the line that dictates the profit within our function, and try to visualize, well, what are the sort of conditions on what the profit could be and how that would look. But basically, if we solve this equation for y, which is the thing the book does next, so if we were to subtract 4x to the other side and divide by 6, what that would give us is negative 46x plus p over 6, and 46 would reduce to 2/3. So basically, if you take this equation, solve for y, we get the same profit function, but we can now look at it as a linear equation. And what we can see about this linear equation is that the slope is negative 2/3. And why this is useful is because we can visualize. So one thing we don't know is what the profit is, but this equation generates of what we call a family of functions, which is just a lot of different isoprofit lines. And I'm going to use a document which I created or a template which I created in GeoGebra to try to illustrate isoprofit lines, because the book does this, but I don't know if it's a little bit hard to understand in the book's context. So I think that an animated example will help, which is why I'm going through the trouble of doing this video really in the first place. But basically, notice that what I have graphed here is, let me move this so you guys can see it a little bit better. Sorry, I'm a little disorganized. I'm so tired right now, but I'm going to get this done. But what we can see is what I have graphed is the three inequalities from before. Basically, each of those three constraints, x plus y must be less than or equal to 100. I didn't actually shade it in, but basically this region down here was our feasible region all beneath each of the lines. I just didn't shade it. And they're also dotted not because of the inequalities, but just because. But basically what I wanted to show you is the isoprofit line. So down here what I have graphed is that profit function where P is something we don't know, but I've created a little slider here so we could play around with the profit, because this is what we're trying to figure out. What is the maximum profit that we could get? And it's based on the number of X and Y can openers that we have. And that's all. And ultimately what we want to do is figure out the maximum profit. And the question is, how do we know what that would be? But there's a very important idea, which is the thing I wanted you guys to see. And so if I'm looking at the different potential for profit, like anytime the isoprofit line intersects with the feasible region, these are all different possibilities, situations which are viable. So like, for example, say I wanted to produce 40 of each type of can opener, that would intersect with my isoprofit line right there. And I could figure out, well, how much profit would I get for producing 40 and 40 can openers? Oops, I went a little too far. But basically, I think that would be $400, which would be my isoprofit line. Now that's not the highest amount of profit, because if I keep going, I can see that there's more points where the feasible region intersects with the isoprofit line all the way up until a certain point. But notice if I set the profit to be too high, it gets out of my feasible range, and there's no range of possibilities for the isoprofit line to intersect with the feasible region. And so what I wanted to show you is that there is a point in which there's like a maximum endpoint to which the isoprofit line intersects with the feasible region, and it always is going to happen at a corner point on your feasible region. So notice that in this particular case, we can get the line to intersect at just A, and it's like the very, very highest point that isoprofit line can touch the feasible region, right? Because if I go any lower, there's plenty of different options, but if I go any higher, there's nothing else that will work. So it's like this is the very boundary point, and basically this will be my maximized profit. So in doing all this and building all this, I can figure out, well, okay, the best profit I could get in this situation is $520, and it will happen at exactly this point, to when I sell 40 manual can openers and 60 electric can openers. And that should fit all of the other parameters, because that's what these other lines represent. It's kind of beneath each of those lines, so it's good to go. And after all this is said, there's actually a very simple way of doing all this. So if you're wondering, do I have to do all this math every time I'm solving these problems? No, there's a very cool shortcut in that, but I wanted to make sense why that shortcut works, because that's the only way we would ever remember all of these procedures, is if we can really grasp the why in these problems. And that's what the book goes into next. It graphs a series of isoprofit lines, but I kind of liked the animated version of that. And the maximum profit line, we can see, intersects the graph at A. And really, that's how we could determine what our best optimal solution would be. So we've really already solved this problem, but there's a very important rule that I wanted to read and make clear to you, because we're going to be using this as we go forward in the next few examples. But what it says is a linear function defined on a non-empty bounded feasible region, and if a bounded feasible region is just a region which is like, it's not going to infinity, it's just stuck together between a bunch of lines, is kind of bounded. Whereas non-bounded or unbounded would just be one that is going up to infinity, is not boxed in. Technically, you could have an empty feasible region, but that is a problem we can't solve. But basically, what it says is that a linear function defined on a non-empty bounded feasible region has a maximum or minimum value, and this value can be found at a corner point. So by corner point, it just means that it has to be one of the vertices to the polygon. So if we're looking at this shape, it's got to be one of the points on the edge. So it could be either A, B, C, D, or E. And that's a different way of going about finding it. So like without, even if we didn't want to think about the isoprofit lines, because that's all kind of complicated, when looking at this region, what I know is that one of these points has to be the best answer. And another question is, well, why is that true? But if you're thinking about the range of different isoprofit lines, if you think about it as sort of scanning through the graph and the maximum always kind of being on the top, notice that it's got to be at one of the tipping points. And the only thing that would change is, well, it could the isoprofit line could have a different slope. And notice if I change the slope, it would actually change the maximum point where the isoprofit line connects back to the graph. Like notice if I change the profit function a little bit, that would change the look of my isoprofit line. But like if I change it to this, the red line intersects the tipping point of the feasible region at a different point. So it could be at E, it could be at B. It just really depends on the isoprofit line. But what's way simpler, instead of having to worry about all that crap, you just know that it's got to be one of those points, and that's how we go about solving these. Basically, we find all the points, the corner points to the feasible region, and then we can plug them into the profit function. And that's what the book goes into next, is if we find all of those corner points, A, B, C, D, E, we could then plug them into our profit function, which was known, figure out the profit, and then whichever one comes out to be the highest is our optimum or optimal solution, which if we plug in each of those 5 points into 4x plus 6y, we can see that the profit for point A is higher than all the other points, and that's another way we could figure this out. So in summary, if you don't have to really worry about all the isoprofit lines and all that business. What you want to do is first find your constraint equations, graph them all up, then find the corner points of them. So basically figure out what's my shaded region, find the points at the ends, and plug those into your profit function. And if you do that, you can figure out the optimal solution to these linear programming problems. In the next video, I'm going to do more of an algebraic example, and then in the last one, I'm going to do another word problem, which the word problems tend to be very difficult because there's a lot of information and a lot to do. And in your try it yourself quiz, it took me quite a while to write a decent problem, so hopefully that one can walk you through some of the steps. And of course, I'm always here on Tuesdays if you need help or if you want to ask questions. And what I'd strongly recommend is read the book, try to learn the terms, and spend a lot of time practicing these sections because they are very, very different than what you see in a lot of algebra classes, and it's very, very applied to business problems. But as you can tell, we can see the use of this very, very helpful to try and figure out what is the best possible outcome given a realistic scenario and given constraints. Very, very realistic situation. Anyways, see you all next time.